All right, today we're taking on graphing quadratic functions in standard form. So first up, we're looking at our function that is in this structure. So we have ax squared plus bx plus c. So we think of the a as our quadratic coefficient, b is our linear coefficient, c is our constant. So we can have a quadratic equation that only has this term. I could have just these two. I could have just these two, or I could have all three terms and it's a quadratic function. But what it has to have the ax squared portion to be quadratic. All right, the graph opens up when the a value is more than 1. So when it's positive, we see a quadratic function, the parabola that opens upward, just like this. When the a value is less than 0, when it's negative, it would open downward like this instead. So an upside down parabola. Okay, the y-intercept, we're looking at the value for y, right, where it slices through the y-axis. We know that the x value will be 0 when we're looking at the y-intercept. So its location here is at 0, c. The x-coordinate of the vertex, so here's my vertex. Here it's the minimum value of my function. So my vertex right here, right where that little u part is, that little dot right here, to get to the x value, negative b over 2a, and then we plug in to find the location for the y. Okay, the axis of symmetry, it's always a vertical line, and it always slices through the vertex, so it's exactly the same as the x-coordinate of the vertex right up here. Okay, if we're getting x-intercepts, so we're looking at where does it slice through the x-axis. So my x-intercepts would be right here and here. Those two locations are when the y value is 0. So we plug in a y value of 0, and then we solve for the x values. Okay, y-intercept, we already covered that, but again, we plug in 0 for the x, and we solve for the y, and that would get us the location that's right here. All right, our first example. Let me slide this up. For each quadratic function, identify the vertex, the axis of symmetry, the x-intercepts, the y-intercept, and graph. So it should be singular. It should be just one y-intercept. Let me correct that right there. Okay, so here we go. If I write out the standard form, it would be y equals ax squared plus bx plus c, just like that. Okay, so we know that the a value is 1, the b value is 2, and the c value is negative 8. So to get to my vertex, I know that x equals negative b over 2a. So in this context, that would be a negative 2 over 2 times 1. So negative 2 over 2 is negative 1. So I know that the x-coordinate is negative 1. To get to the y, I need to plug that in. So y equals, I'm going to always plug it into parentheses, negative 1 squared plus 2 times negative 1 minus 8. Okay, so now as I work through my order of operations, negative 1 squared is 1, and then minus 2 minus 8. So 1 minus 2 is negative 1, minus 8 is negative 9. So here's the location of my vertex, negative 1, negative 9. So if I add that to my graph, negative 1, negative 9 is right here. Big old dot for the vertex. Okay, the axis of symmetry, remember it's always a vertical line, and it's always going to slice through the vertex, so it's going to take this value right here. So x equals negative 1. Just to remind you, it's that same equation of negative b over 2a. We already solved for that, right? And we got that x equals negative 1. So if I add that, let me just find my ruler right here. If I add that line of symmetry, it goes right here. So here is my mirror line, my line of symmetry, my axis of symmetry. Okay, now I need my X-intercepts. So I know that those occur when the Y value is 0. So I'm going to set my equation equal to 0. So 0 equals x squared plus 2x minus 8. So again, all I did was plug in a 0 for the y in my original function. So now I have an equation that is set equal to 0. So now when I think about, well, how do I solve my quadratic equation for x? I got some options. I can try to solve by taking the square root. That would not make sense here because I have a linear term. If it looked like this, I could solve by taking the square root instead. Can I factor? I would try to factor this one. I'm looking for two numbers that multiply to a negative 8 that add to a positive 2. If you like to picture that, off to the side, here's my product, here's my sum. So my product is the negative 8 and my sum is 2. So I have to multiply to a negative 8 and add to a positive 2, right? It's got to be 4 times negative 2. So those are my factors. I have x plus 4 times x minus 2. And when I solve, set each factor equal to 0 and solve for x, I get negative 4 and positive 2. Okay, those are both values for x when the y value is 0. So as points, I would write those as negative 4, comma 0, and 2, comma 0. I have to always write them as an ordered pair because they are locations on my graph. So if I add a point here at negative 4, 0, and here at 2, 0, what I can notice right now are that those two X-intercepts, they are equidistant from my line of symmetry, right? Right here, 3 units, and here, 3 units. So I can always just kind of check to anchor myself that I'm in the right position. Okay, lastly, Y-intercept. Well, that occurs when the X value is 0. So if I go up to my original equation and I plug in 0 for all of those X's, watch what's going to happen. Y equals 0 squared plus 2 times 0 minus 8. Right here and right here, those both clear away to 0. I'm left with the constant at the end. So my y value is just negative 8. So again, my y-intercept is a location. It's got to be at 0, negative 8. And if I add that to my graph right here, there is my y-intercept. I usually add its reflection point right over here just to help me smooth out my curve. Now that I have those points plotted, I just want to remind you of your quadratic parent function and what it looks like. So if we started our vertex, right, with our parent function, we're usually at the origin, but we start at the vertex and we go over 1, up 1, both sides, back to the vertex. We go over 2, up 4. So I have a point here and its mirror point here, back to the vertex. If I went over 3, I'd be going up 9, and that's the location right here. Left 3 up 9, that's the location right up here. So I see that even though I'm in a different structure, I still have points that fit the parent function pattern. So I'm ready to connect my dots and smooth out my curve for my quadratic function, right? We know it's nice and U-shaped. It's a beautiful parabola. Okay, next sheet. Okay, so here again, same instructions. For each quadratic function, identify the vertex, the axis of symmetry, the X-intercepts, and again, this should say Y-intercept. There is only one, and then we graph it. Okay. So here we have y equals negative x squared plus 9. So here, let me remind you of my structure. y equals ax squared plus bx plus c. So what's interesting here in this variation is that I have a quadratic term. The a value is -1. I do not have a linear term, so the b value would be 0. And then my constant, the c, is 9. So when I go after my vertex, watch what's going to happen. I know that it's x equals -b over 2a. So x equals, well, -0 over 2 times -1. So if I have 0 on top over anything on the bottom, it's going to simplify to be 0. So the x-coordinate of my vertex is at 0. Now I have to find my y. So if I plug in a 0 for the x, so -1 times 0 squared plus 9. Well, 0 squared still 0. 0 times -1, still 0. So I end up with a y value of 9. So my vertex is at 0, 9. Let me plot it right up here. Okay, there is my vertex. I can see that it's on the y-axis. So my vertex is actually also my y-intercept. So I'll add that right here, 0, 9. When I plug in a 0 for the x, the y value is 9. So again, I already know that's that location. Okay, my axis of symmetry, remember it's just x equals -b over 2a. It is an equation for a line, a vertical line, so it's always x equals a constant, and it's always the same x value as the vertex. So x equals 0. Okay, I'm going to take my ruler, draw in my axis or my line of symmetry. So there we go, that's my mirror line, my axis of symmetry. And now I need my x-intercepts. So here I want to remember that the y value is 0. So if I plug in a 0 for the y, I have 0 equals -x squared plus 9. Okay, so for this one, when I run through my list of ways to solve, I could solve by taking the square root. That would work here because my linear term, right, I don't see anything with an x, right? It would be 0x for that b value position, right, for my linear term. So b is 0. So here I could solve. I could take away the 9. So -9 equals -x squared. Okay, I'm trying to solve by taking the square root. Divide each side by -1. So now here really I have x squared equals 9. Now I can solve by taking the square root, and I get that x could be plus or minus 3. So my x-intercepts would be at 3, 0, and at -3, 0. Okay, but I want to show you another way that we could have solved this one. I could have solved it by factoring. So 0 equals -x squared plus 9. So I could see, oh, there's a -1 out in front. Let's factor that out first. We always treat a -1 in front of the x squared as a GCF. So I'm going to divide out that GCF first. So -1 times x squared minus 9. So now I can see, oh, it's really a difference of two squares pattern. I can break this down further. X minus 3 times x plus 3. So I have right now -1 times the quantity of x minus 3 times the quantity of x plus 3. So then I can set each factor equal to 0 and solve. So setting a -1 equal to 0 and solving, there's no x there, so I get no solution from here. If I set this one equal to 0 and solve, I would get a solution at x equals 3. And if I set this factor equal to 0 and I solve, I would get a solution at x equals negative 3. All right, so if I add those two locations, the negative 3 and the positive 3, just like that, I see that I have a parabola that opens down, right? My quadratic function, that leading coefficient was negative. So instead of having a U shape up, right, it's an upside down U. Let me check the parent function pattern. So from the vertex, if I go over 1, I'd be going really down 1 here and here. Okay, go back to the vertex. Over 2 and down 4 would put me here and here. Okay, back to the vertex. Over 3 would be down 9. Boom, right there at that X-intercept up here. Over 3, down 9. Perfect. So I know I see that parent function pattern. I am good to connect my dots and draw in my quadratic function, my upside down parabola. Okay, one more problem. All right, in C here, again, it's a quadratic function. Y equals ax squared plus bx plus c. So in this one, I do have a quadratic term. I have a linear term, but my constant is really just 0. So let's start. Vertex. X equals negative b over 2a. So x equals negative times negative 5. So negative 1 times negative 5 over 2a, 2 times 1. So here I get positive 5 over 2. I get 5 halves, or 2 1/2. Right, I'm just getting a fraction here. So 5 halves. That's okay. We know what to do. Okay, for the y value, we need to plug in the 5 halves. So 5 over 2 squared minus 5 times 5 over 2. Okay, so if I take 5 over 2 squared, that's 5 squared, so 25, minus 2 squared, which is 4. So I have 5 squared is 25, 2 squared is 4. Okay, and then over here, we're looking at negative 5 times 5 over 2. So here we get 25 over 2. Okay, so we have 25 fourths minus 25 halves. So here I need to have a common denominator so I can go forward. So here if I multiply this side by 2 over 2, right, I can multiply any ratio by 1 and preserve the ratio. So 2 over 2 would reduce to 1. So now what I have is 25 over 4 minus 50 over 4. So I get negative 25 fourths. So negative 25 fourths. So here's my vertex. Right, I wrote it as an improper fraction. Let's say I want to convert it into a mixed fraction. Makes it a little easier for me to graph. So 2 goes into 5 2 times with 1 left over. So 2 1/2. Okay, for the y, 4 goes into 25 6 times with 1 left over out of 4. So here is what my vertex looks like as a mixed fraction. So I'm looking at 2 1/2 and then down 6 1/4. So right about here. There is my vertex. Okay, my axis of symmetry, x equals negative b over 2a. Remember, it's going to be exactly the same as the x-coordinate of the vertex. So x equals 5 over 2. You just have to remember to write it as an equation. And it's an equation for a vertical line. So x equals 2 1/2 or 5 halves. Either structure is fine. Let me draw it in. Okay, so there is my axis of symmetry. My x-intercepts, right, the y value is 0. So 0 equals x squared minus 5x. So if I run through my list, I would not solve by taking the square root. I do have a linear term here. Okay, next up, can I factor? Well, yeah, I can factor. I have a very easy to see GCF. That GCF is simply x. So 0 equals x times x minus 5. Okay, take each factor, set it equal to 0, and solve, and I get here that x equals 0, and here x equals 5. Oops, didn't need the parenthesis anymore. X equals 5. There we go. All right, so as points, I would say 0, 0, so right at the origin, and my other one will be at 5, 0. So if I plot those points, so right here at the origin, and at 5, 0 right here, you can see that those locations are still equidistant from that mirror line, from that line of symmetry, right? They are both 2.5 units away from that line of symmetry. Okay, lastly, my Y-intercept, I know that that's when x is equal to 0. So if I plug in a 0, well, I actually already see it, right? Y equals 0 squared minus 5 times 0. Right? Those both wipe out to be 0. So it just confirms that it's at 0, 0. I already saw that point right here at the origin. I actually knew that that had to be my Y-intercept already. So 0, 0. All right, so I have enough information to smooth out my curve, just like so. Oops. Gonna clean that up just a little bit, just like that. All right, and there we go. All right, I hope that was a good introduction to graphing quadratic equations, functions in standard form. Have a good rest of your day.